Hello students. So in the previous class I have discussed how to formulate the expression for the delta connected load filter currents to compensate the source current. So basically in the previous class we have established that IFAB star equal to ILAB minus AC 31 by A matrix determinant of A matrix A delta for delta configuration into PL average. I hope you remember this. And similarly we have IF BC ILVC minus AC 32 by A delta PL average, and IFCA star equal to ILCA minus AC 33 by A delta into PL average. Do you remember the value of A matrix, A delta matrix for this particular case, for this delta connected load configuration? I'll write here once more. The matrix A delta was defined as, from the three conditions we got from the previous formulations. Remember, the first is 1 and 1. Okay. Then you have second row. The second row consists of the voltage elements. Okay, I'll put here. The second row was here BSC minus BS0 or BSA0 plus B beta into BSA minus BSB. We have done the last class. If you go through, you can find that. Similarly, if this is BSA minus BS0 plus beta BSB minus BSC, and this is BSB minus BS0 plus B beta BSC minus BSA. Okay, and third row was corresponding to the power. The multiplication of ISA into BSA and so on is equal to PL average, which transforms to this equation: BSA minus BSB, BSB minus BSC, and BSC minus BSA. Okay, this into, of course, current matrix equal to this side power column matrix. This was the A matrix, A delta matrix. So we have to find now the determinant of this matrix, that is A delta, okay, and the cofactors of this matrix AC31, AC31 AC32 and AC33. Then substitute these values in these current expressions. We will find the reference filter currents placed between line to line of the delta connected load, these three currents. Clear? So how to find this determinant of this? Same procedure. We can write like this is A11 element, this is A12, this is A13, this is A21, and this is A22, this is A23, this is A31, A32, and A33. Then obviously the determinant of this matrix is given by A, here A delta determinant is nothing but just take factor A11 and multiply A22 into A33 minus A32 into A23. Then minus A12, this factor, then A21 into A32 minus A31 into A22, and then this factor plus A13 into A21. This should be actually A33, not this. Please correct this. This is A33. This into this, so this is A33, and this is 32 into. I'm sorry. Please again do it again. So this is the second factor. So this A21, correct? A21 into A33. So A33 minus A31 into A23. Okay. And then 13 comes here. Then A21 into A32 minus A31 into A22. Okay, substitute these values and simplify them the same way as we have done for previous case. Then you will get, after simplification, as the negative of determinant which you have found earlier for three-phase four-wire system. In the previous class, I think 2 classes back, we have found determinant of the matrix for three-phase four-wire system by putting these conditions and solving for currents. Okay, same matrix, the value is same, but it has a negative sign. Please prove this by yourself. So basically, I can write that this is equal to either BSAB square plus BSB square plus BSC square minus sign, because this was A was this one, so minus sign has come here, or minus 3 BSJ square minus 3 BS0 square. This is sigma term where J equal to ABC. Close this whole bracket. Or this is also equal to minus 3 BSJ minus Bs0 whole square sigma J equal to ABC2. Okay, so no difference except the negative sign. So this determinant and the previous determinants, the difference is only of negative sign. Value wise they are same. Okay, so once we know determinant, we shall find out the cofactor transpose. The cofactors transpose will come from this matrix. Okay, so let the cofactors of this matrix be AC31, AC32, and so on. Okay, just last time I said that only AC31, AC32, and AC33 are going to play role because of zero element in the power column matrix. So only what is important is this term and this term, this term, and this term. Okay, only these cofactors are important while solving these currents. So we will directly go to these factors and write here what is A, C, 3, 1. What is that? This is a cofactor for third column first row. And what will be this? This is cofactor of this element. This is 3 by 1. So I have to take this matrix, this row and this row I have to delete, and I have to multiply this into this minus this into this. Okay, and therefore this cofactor is given as BSA minus BS0 into this plus beta BSB minus BSC and the whole bracket here. Okay, so 1 into this should be 1 into this. So should come first, not the second one. I'm sorry, we change it. What you get it here, this is from 1 into this and this into 1. This also you need to change those directions to be proper. This into this minus this into this. Okay, so we will therefore get it here. This becomes BSB minus BS0 and then plus B beta into BSC minus BSA and then again minus this one. So BSA minus BSC, BSA minus BS0 plus beta into BSB minus BSC, close the bracket. Check me if I am correct. Okay, is that fine? Now we collect the coefficients of the beta and non-beta terms. So this is equal to here, this is BSB minus BS0 and from this you get minus BSA and minus minus plus Bs0. So Bs0 will go away with this. And then I take beta common here. This becomes Bsc minus Bsa, and minus 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 Bsb will come here, and minus minus become plus Bsc. Correct? Now this becomes 2Bsc. So this and this term make 2Bsc, and we have a minus Bsa minus Bsb. So here we will add one more Bsc and subtract one more Bsc. So this becomes minus 3Bs0, zero sequence voltage, and this becomes 3Bsc. So 3Bsc minus 3B0. Take 3 common. So this is beta already here. So this whole term become 3 beta Bsc minus Bs0. And this side it is Bsb minus Bsa. Right? So we will take here minus common to make it Bsa minus Bsb in the sequence of AB. Since minus common is everywhere, so this becomes actually minus 3 beta. And close this bracket. So this is the factor AC31. Am I correct? Check me. This is the factor AC31. Similarly, we can find out AC32. Now, it must not be difficult for you to guess what is AC32. Same thing, advance one more subscript. So Bsb minus Bsc, close this bracket, and minus 3 beta Bsa minus Bs0. And similarly, we can write for AC33 equal to minus Bsc minus Bsa minus 3 beta Bsb minus Bs0. Okay, so there are basically 3 cofactors, and their values are given by these expressions. So we know the determinant and we know the cofactors. Average load power has to be computed. Substitute back into the previous expressions of the currents, that is IFAB star, IFBC star here, and IFCA star, those points, and simplify them. Okay, so let us go and substitute these values back. So therefore, what is IFS star? I'll put here. So therefore, IFAB star is nothing but ILAB minus AC31 is this, so minus VSA minus VSB whole bracket here minus 3 beta, okay, BSC minus BS0, close this bracket, into PL average and divide by determinant of that matrix. What is that? Minus 3, let us say, second variant, sigma bsj square. So this becomes bsj square minus 3 bs0 square. Close this bracket and put sigma j equal to a b c. Then you will see that negative sign goes with this negative sign. Okay, negative sign goes with this negative sign, and 3, if you want, you can put it here or you can leave it. It's up to you. So if we leave 3 as such, it becomes simply ILAB minus this minus BSAB. It's line to line voltage because this is line to line configuration, so I can write this as VAB, and minus 3 beta VSC minus BS0 by 3 will come here, and sigma VSJ square minus 3 BS0 square. Close this bracket, substitute J for ABC. This is IFAB star, and into of course PL average. So this into PL average, and same way we can write for IFBC star, the reference current for branch BC equal to ILBC minus VSBC minus 3 beta VSA minus VS0. Just advance subscript by 1 and you will get the next expression, VSJ square minus 3 VS0 square. So this sigma here, J equal to ABC into PL average. Fine. And the third will be IFC star. So this is IFC star, IFC star equal to ILCA minus VSCA minus 3 beta VSB minus VS0, correct, divide by sigma BSJ square J equal to ABC minus 3VS0 square. So this bracket, put 3 here into PL average. These are 3 important equations, and these are therefore equivalent to the expression for the reference compensator current, line to line reference compensator current for delta connected load. The nature is similar because you can see that IFAB depends upon the ILAB and the voltage parameters up and down, the numerator and denominator, and the average term. If you compare with the previous, the denominator and numerator are slightly different. In denominator we have 3 additional, and in the numerator it was BSA minus 3 plus beta, was plus here beta, BSB minus BSC. Okay, so there was slight change in these 2 components, this component and this component. Okay, these 2 components for each phase. We can make some simplification in a similar way we have done for three-phase four-wire system. Okay, we can assume that three-phase voltage are balanced. So I will say three-phase voltages are balanced, and hence that implies BSA plus BSB plus VSC equal to 0, and they are of fundamental frequency. Of fundamental frequency. Okay. So this means BS0 equal to 0. This is first condition. Second condition, we can say we want to compensate for unity power factor. For unity power factor. That means beta equal to 0 because beta is nothing but 10 phi plus y root 3, and phi plus the desired phase angle between the positive sequence of phase A and current after compensation. Now, if we substitute these conditions back into this expression here, then we will get a new expression for these currents, and this becomes IFAV star equal to, what is there? ILAB minus, now this is 0, beta is 0, and this is 0. Okay, so it becomes VSAB by 3 sigma BSJ square J equal to AB J equal to A, there is some slip in my hand, please correct it. So J equal to ABC into PL average. Okay, this is what we will get it. And similarly, IFVC star equal to ILVC minus BSBC by 3 into sigma BSJ square J equal to ABC PL average. And finally, IFC equal to IFCA equal to ILCA minus BSCAY sigma BSJ square J equal to ABC 3 here and 3 If you look this more carefully, okay, then you will further observe that sigma BSJ square, last time if you remember we have computed this term, sigma BSJ square for valence voltages equal to 3B square. We can prove that. So this term is equal to 3B square. and 3 is this, so 9V square. Okay, so finally we will get the expression of the filter current as I FAV star equal to ILAV minus VSAV by 9 V square into PL average, and then IFVC equal to ILVC minus BC line to line voltage by 9V square PL average, and IFC equal to ILCA minus VSCA by 9V square into PL average. Okay, is that making sense? Sense means that whether it is matching our the common sense of understanding this particular thing. What common sense says, if I compare this scheme with the previous scheme, it must be equal to basically star delta transformation. If the previous case is star, then this is delta, is it? If the previous scheme is star, then it is equivalent to star to delta transformation. In the previous scheme, we found that this ratio of this to this was 1/R equivalent. 1/R equivalent. Now, if you think that there is a three-phase four-wire system or star-connected load with a R equivalent resistance between AN neutral, BN neutral, CN neutral, and if I transform back to delta, then it will have the resistance of 3R EQ. Remember? 3R EQ. And what was this actually REQ? It was nothing but the ratio of PL average by 3 by V square. Now we have PL average by 3V square, or you can say this was 1 by V square by PL average by 3, and this is R equivalent. Now we have 3 here. Instead of 1, we have a 3 now here. So therefore it becomes 1 by 3 R equivalent, which is correct, because if this reflects delta connected load equivalent to the previous one with the same power, then it must be the thrice of. If you convert the delta into star, the resistance between A and B becomes thrice of that. Okay, and this is line to line voltage. So basically this is kind of a line to line current, ISAB star, okay, which is nothing but VSA in phase with the VSA. So this further equals to, if you want to simplify further, then you can write IF AB star equal to IL AB minus BS AB by 3 R EQ, or you can say this is the R equivalent for delta, or R equivalent delta into PL average. And same is true for this, which shows that the current ISAB after this compensation is in phase with this voltage. Therefore, the compensated currents are in phase with the voltage. Now I will go back to the textbook, the book which we are referring, NPTEL book on power quality, unit 5th, and consider the example 5.6. Okay, and with this example we will complete this unit as well. So I will go to that part and try to see a question. So let us go to that section and come here. This is 5.2 example. I will make it bigger now. So go to the view and make up the size. Okay, F11. All right. So this example is about the three-phase, three-wire system here. Okay. Five point six. So this is example 5.6. Consider a three-phase balanced system on figure 5.10, which I have already discussed. The supply voltage are VA is 230, 0, so they are like reference phases, VB and VC. The impedances for delta connected loads are ZAB is this, VC is this, and CA is this. So they are unbalanced three-phase delta connected load. Now using instantaneous symmetrical component theory, we have to compute the line source currents ISA, ISB, ISC without any compensation, and then find the reference currents IFAB, IFBC, and IFCA for ideal compensator so that the source currents are in phase with the voltages and with unity power factor. Also find out the active and reactive components of the powers for the compensator, and based on that identify the nature and values of ZAB, ZBC and ZCA if we realize them using the physical circuits. Okay, similar to what we have done previously. Find out the expressions for the currents based on the filter currents for the source currents and check whether they are in phase with the system voltages. And also find out the powers to prove that the source supplies only the real power and QS is equal to 0. Okay, so almost we have similar steps that we have done for the previous example, and since it is only the fundamental quantities are being involved, only one frequency component is there, so we therefore can use the phasor expressions for that. So first we find what is ILAB, what is ILVC, what is ILCA. Okay, it's a line-to-line voltage by the impedance, and we calculate. This comes out to be 30.64 minus 37.38 amps. And then the second phase is BSB by ZLVC, and we substitute these values. we found that it comes out to be 79.69 angle of minus 143 amps. And third phase, ILCA is nothing but IBSCA by ZLCA. This comes out to be 22.52 minus 162.71 amps. So what is ISA? ISA is nothing but ILAB minus ILCA. Remember this expression? Can you recall it? From the Kirchhoff current law at point A and B and point C at the east corner of the delta connected load. And these currents are, you can see, they are quite unbalanced. This is the R phase, this is the Y phase, and this is the B phase, RYB. Okay, they are quite unbalanced in magnitude as well as in phase angles. Okay, so they are unbalanced in the respect of magnitude and phases. And we can therefore form the real-time expressions for these currents. Okay, so these are here. ISA, ISB, ISC. So this is the R phase. ISA in time domain. This is ISB in time domain. And this is ISC in time domain. Now we have to find the reference filter current so that the source currents are balanced. They have a same magnitude. They are balanced means these magnitudes are same and the phase angles are having zero phase shift with respect to their system voltages. So we know the expressions for them. Okay, you can recall these were the expressions for the currents. Okay, so we just find out these currents and express in phasor domain because of PM only one frequency component and substitute their values. Now in this, what is the value of PL average? PL average is nothing but the computation of the power of the load. So we can find these components by using this term. In real-time domain, you can find out Y averaging over a cycle 1 by T. Let us say this is T1 minus T and this is T1. So one cycle data is here and this is VS AB into ILAB. You can find out that way. Okay? This is the real-time technique and this we have used the pages for that. Because we are solving analytically, so we can use the phases here, time being. This into dt. So once we know this power, the value of power is here. Okay, and these sigma VSJ square is 3b square, so it's 9b square. So I know 9 into b square is 230 square, and this is the VSAB. Okay, this is the power here. So you simplify this, we'll get the value of the current comes out to be 31.2 angle of minus 64. For the second phase, 67.71. This is IFBC. This is IFA, and this is IFCA, which is 19.17 minus 89.67 degree amps. And from this we can construct back into the time domain. So this becomes IFAB. This is IFBC. And this is IFCA. Now let us find out whether these currents are correct. If these currents are correct and they must keep the source current balanced and in phase with their respective voltages. So let us find out. So IS is nothing but ILAB here minus ILCA minus IFCA. Okay. Similarly for B and similarly for C. And we just compute them and observe that all these currents are basically balanced. You can see 43.22 have magnitude and angle are 0 and minus 120 and plus 120. And therefore again we can construct back in time domain and you can see that these are the currents. Okay, these are the currents in time domain. So the magnitude is 43.22 into root 2. This is RMS value. Okay, this is the RMS value and this is the peak value. Sin omega t minus 120 and sin omega t plus 120. We can also compute the powers. So you can see these powers from the load, from the source, from the compensator. See load power PL and QL 29,824 watts, 30,069 watts. And if we compute the B phase of compensator, it is 0 watts. This means there is no real power involved with this filter. The net real power equal to 0. But the individual phases may have some plus or minus power. Similarly, QF is equal to QL. You can see it here. This QF is equal to this QL. Okay. And PS we compute, then PS is equal to same as PL. So you can see this is equal to PL. This is equal to QL. And this is equal to 0. So QS won't supply any reactive power. The source does not supply any reactive power. So at the if you find out the compensator performance, so what finally we observe? We observe that P S equal to PL or PL average and QS is equal to 0. Therefore, PF equal to 0 and QF equal to QL. So in this way, we are able to meet the requirements of the load powers. At the same time, we maintain the quality of the supply, that the currents are always in phase with their voltages and they're always balanced. Okay, so with this, I am completing this unit of the control theory for active power filters, and please go through all the problems during this time before you come to the institute or whenever the institute opens after 1 or 2 weeks. These problems have to be solved one by one. Okay, so all these questions 5.1, even theoretical questions 5.2, 5.3, whatever I have given in this chapter, consider them as the tutorial for this unit. 4, 5.5, 5.6, 5.7, 5.8, 5.9. There are like 10 problems for the tutorial, so do not leave them. Okay, then all these sections you have to solve. ABCD answers are given. If there is any conflict in answers, please let me know back. I will have some Zoom meeting in the next in this week. And 5.10, okay, 5.11, and so on. You can also solve problem from the other books if you can find out. Okay, so with this, I am completing this unit 5 on the control theory for the load compensation for active power filters. In the next class, I will talk about the next unit and the last unit of this course. It is called DVR, or dynamic voltage restorer, which is a complementary device to D-statecom. D-statecom, or distribution static compensators, compensates the load currents or the currents by connecting it in shunt with the load, while DVR does the dual function, the opposite of this, that is, it compensates the voltages by connecting it in series with the load to ensure that the load bus voltages are maintained at the nominal or standard value and their nature remains sinusoidal. Okay, so basically we are looking for voltage compensation scheme using active power filter. And UPQC, which is called Unified Power Quality Conditioner, is some of these two devices. It has the feature of the load compensation and the feature of the voltage compensation, the current compensation and the voltage compensation. So I will stop here and we'll meet for the next video lecture.